So if we think about what happens with blood lactate in relation to incremental exercise, this is typically what we see. So this is data taken from our laboratory in a study where we worked with, as we can see here, 92 recreational marathon runners, and this is average data from those groups, from our fastest runners who were the sub 3 hour marathon runners to our slowest runners who were running slower than 4.5 hours for the marathon. But what we can see in all of these groups is we can see this traditional curvy linear response. This is the fastest runners that we can see. And this is conventionally what we might see in a textbook, showing this kind of increase in blood lactate. It's a fairly level response, then you get this kind of systemic increase in lactate. If we look at the slowest runners, actually the slowest runners are quite useful for us because despite a little bit of noise in the data, which is occurring around about this point here, what you can see is very much a conventional response. So what you'll notice is that there is quite a quick rise here from 6 to 7 kilometers an hour. Then you get a secondary rise, but notice what happens then. So if we go from 8 kilometers an hour up to 11 kilometers an hour, the rise in the blood lactate concentration is less than 1 millimole, despite the fact we've got a 3 kilometer an hour increase. Once we get to the 11 kilometer an hour point, then we get this sudden systemic increase in the blood lactate concentration, and over the course of 1 kilometer increase, the lactate concentration goes up by over a millimole, and then we get a continued rise up to this point here, where in this group the overall the test was terminated. So this really lends itself to the idea of what we've covered in previous classes, that there is a balance being attained in these lower intensities between the rate of appearance and the rate of disappearance of lactate. So that is what we're assessing in the blood, represents that balance between lactate, which is being produced, and that is being produced in those engaged muscle fibers, and lactate, which is being consumed in the inactive muscle fibers. But also understanding that quite a large proportion of the lactate that's being produced is actually being directed to the liver through the Cori cycle and is being converted back to glucose. And that is really the same process that's going to be happening in our inactive fibers. But just as a brief reminder, as exercise intensity increases, two things are important to this appearance and disappearance. Firstly, we start to recruit more fast twitch muscle fibers which are less efficient. Fundamentally, as we're running faster, we need to generate more force because the muscle needs to contract at a faster rate. Therefore, in order to facilitate that, we progressively increase, in conjunction with the slow twitch fibers, we progressively increase the recruitment of fast twitch fibers. That's important because the fast twitch fibers are our producers of lactate. Not to say that slow twitch fibers don't produce lactate, but proportionally a fast twitch fiber will produce more lactate than a slow twitch fiber. The second thing to remember is that as we progressively increase the exercise intensity, there is a concomitant reduction in the number of inactive muscle fibers. Now, the inactive muscle fibers play an important role. If a fiber is not being engaged in the exercise or is not being activated, it can take up the lactate. It becomes a consumer of lactate. And the predominant consumers of lactate are our slow twitch muscle fibers. So as we start to increase exercise intensity, we will be increasing the recruitment of slow twitch muscle fibers. There'll be some additional recruitment from fast twitch, but not predominantly. But as we're recruiting more slow twitch fibers, because we're having to run at a faster pace, we've got now less inactive fibers. We get to this point here, this transition, where you get this sudden acceleration in lactate, and that fundamentally represents the point where the rate of appearance of lactate exceeds its rate of disappearance, because you haven't got sufficient inactive fibers to compensate for the progressive increase in active fast twitch fibers which are producing the lactate, and therefore we get this sudden increase. And this represents therefore a really important boundary for us. This point represents the boundary between what is predominantly steady state exercise. So anything below this point is defined as being steady state. So if we looked at any of these workloads and we asked our participant to exercise continually at these workloads, you would get a steady maintained lactate concentration, as you would see in the VO2 response and even, for example, the heart rate response. However, as we go beyond this point, we lose the steady state condition. And what we end up with is we end up moving into a series of exercise domains beyond this point, one which is termed heavy, and then we move into one which is termed severe. So anything below this point is moderate. Now, if you're unsure or you're thinking, gosh, that sounds quite interesting, you may want to step forward into another class where within this channel, which is on oxygen uptake kinetics, which may help explain that for you a little further in terms of what those domains mean. But fundamentally, this point represents the boundary between steady state exercise and non-steady state exercise up here. We get a steady state in the heavy domain, but it's a steady state which comes at a cost. It's related, not surprisingly, to the fast-twitch muscle fibre recruitment. So it's fundamentally a really important point for us in terms of our understanding of exercise physiology. And so it represents what we call the aerobic capacity. Now, this is, again, a terminology point. We've discussed in previous classes, particularly the one related to maximum oxygen uptake, that there is propensity within the literature for authors to refer to VO2 max as max aerobic power. But as we described, the unit for VO2 is rate-based. It's mils per kilogram per minute. The unit for lactate is not rate-based. It's millimoles or millimoles per litre, or we would simply have this as, for example, maybe the percentage of VO2 max. They're not rate-based. So this represents the capacity to work under steady state conditions, predominantly aerobic conditions. And if we go back to kind of the work from George Brooks, who's very much kind of the godfather in terms of our understanding of lactate exchange during exercise, I think it's just worth reiterating and restating what he wrote, which is this. Once thought to be the consequence of oxygen lacking contracting skeletal muscle, we now know that lactate is formed because it is the product of glycolysis. But lactate is utilised continually under fully aerobic conditions. So this relates to the notion that if we are in a steady state condition, the amount of lactate that is being produced from the active fibres is near as damn it being matched by the amount of lactate being consumed in those inactive fibres. Hence you get that steady state condition. Working skeletal muscle simultaneously produces and uses lactate as fuel, with much of the lactate formed in glycolytic fibres being taken up and oxidised in adjacent oxidative fibres. So this is fast or slow. Lactate disposal is mainly through oxidation, especially during exercise, when oxidation accounts for 70 to 75% of removal and gluconeogenesis the remainder. So that's a really kind of important clarification of what we've been defining already when we were looking at that data from our marathon runners. Now, this is data from a textbook I wrote on coaching science, and this is data from a Paralympic athlete who we tested in our laboratory. And it's really useful because this is a really nice representation of what physiologists, particularly those working in the performance side, would generally be looking for to help monitor athlete training and also potentially prescribe training zones. What we can see on here is that there are two discernible responses. Now here's the first one, which is perhaps the most obvious one. So this is what we've already been referring to. This is the transition from steady state. So again, how do we know it's steady state? Look at the lactate concentration from 11 to 15 kilometers an hour. So you've got a 4 kilometer an hour rise in running speed, yet the lactate concentration has barely shifted. It's gone from about, let's call that 1.6 to maybe 2 millimole per litre. It's almost no change. So that absolutely defines our aerobic capacity, or our transition from steady state to non-steady state conditions. It's not truly non-steady state just above this point. As I say, once you're in a heavy domain, you can get steady state conditions, but once we go into the severe domain, it's absolutely non-steady state. There is a second point that is on this graph, which is less obvious. And so you can see, and it's not because we've got this downturn in the lactate concentration here, it's fundamentally representing this first initial rise in the blood lactate concentration here. And this really represents the point of where we start to get an appearance of lactate in the circulation. Now, you may be asking, well, hold on, you've got an appearance here. But this appearance here is almost certainly a manifestation of inefficiency in running. Let me explain what I mean. So the athlete that we've got here was a world-class Paralympic endurance athlete. So the data that you see here is taken from a 3-time Paralympic gold medalist and world record holder in distances really ranging from the 1500 meters right the way up to the 10,000 meters. So their running speed, their actual racing speed, is actually way above 15 kilometers an hour. When you look at, for example, the times they were running from really 10K, which is a great example. So they don't really run and train down here. So when we asked them to run, and we did this because when we first tested the athlete, we weren't really sure where we were setting the boundaries in terms of working with them. So we generally like to start the tests at lower speed so that we don't miss this first lactate response. So we start them at slow speed. The net result is that they are actually not very efficient at these slow speeds because that's not where they train. And because they're not very efficient, it alters what they're doing mechanically. So the biomechanics change. And because the biomechanics change, it changes muscle fiber recruitment patterns. So the net result is they over-recruit fibers and therefore produce perhaps more lactate than one would anticipate. As we start to get them into the running zones where they do start to work, and down here this might be what we call easy exercise or recovery-based exercise, the lactate concentration drops and now starts to really represent the first appearance of lactate from the cell into the circulation. And you get this very gentle little rise here. So it's quite a hard point to discern. Then we go into this period where we get this steady state response, and then you get this non-steady state response that you see here. So we have these two points. Now, how do we define these? First way to define these is what we call LT1 and LT2. So the first lactate response and the second lactate response. I'm being slightly cautious in the language that we're going to use here. Now, from here on, this class is only going to focus on this point here, because fundamentally this is the most important point within the field of exercise science and exercise physiology. And secondly, this is actually really quite hard to determine with precision, because so much of this will depend, as you'll see, on the precision of your lactate analyzer and the degree to which your analyzer is calibrated, but also the fidelity in the data. Whereas this is a much more robust response. So we're going to focus on this. So how do we then